The first gas law we're going to talk about is Boyle's law. Boyle's law looks at the volume-pressure relationship. The idea of as you push down on this container that you see here, this piston if you will, the space that these molecules get to interact with decreases. So we just decrease the volume. And what happens to our pressure? If you remember back to the kinetic molecular theory, that first law, it says the container only knows about the different pool balls that interact with it, the ones that collide. And that's what pressure is. It's force over area. And so as you're doing this, these balls, these atoms, are going to interact with its container a whole lot more just because there's not as much space for them to move around in. And so just due to the decrease in volume, that pressure is going to increase because it's having a lot more collisions. Now the things to note on this law is that it's a constant temperature and a constant N, where N stands for the moles of that gas. I sometimes will use a Capri Sun to illustrate this law, not because it's a gas, it's a liquid, but it's kind of the same principles. What happens if you stick your straw in and then you squeeze the container while you're sticking the straw in? I'm sure everybody's had this happen to them. That liquid just comes out everywhere. And so as you're increasing that pressure, the volume doesn't want to be compressed. It's not a gas, and so it's going to want to expand somewhere. And so it's that same idea. You are trying to expand it. You're decreasing that volume, which is increasing that pressure. Boom, getting you Capri Sun everywhere, and you're all nice and sticky. Another example that illustrates this is scuba diving. Let's say a scuba diver is at atmospheric pressure, so that it's 1 atmosphere. As they go down and down and down, they're having more pressure on their body, simply due to all of that liquid above them. All of the ocean is now pressing down on them, whereas before they only had the upper atmosphere, the gases that were pushing down on them. Now all of that pressure from all of the water above them is pushing down. So the pressure is increasing. As you increase that pressure, then Boyle's law says increase pressure, decrease volume. And so your volume is decreasing. A volume of what, you may ask? That would be like your lungs. And so one of the big problems is if you go scuba diving and you aren't trained properly and you try to come up for air too quickly, you submerge too quickly, you can have significant damage on your internal organs. And the reason for this is Boyle's law. That's because as your pressure is decreasing as you're going to the surface, your volume is increasing. And so it's inversely proportional. Decrease that pressure, increase that volume, and so your lungs are going to literally expand to 3 times their previous volume, and that just doesn't fit in your chest cavity very well. There's also another law that explains that, and that is Charles' law. The idea of as you increase your temperature, your volume also increases. So it's these 2 laws that really correlate to keep you safe. If you know them and you understand the physics of them, it can help make scuba diving a much safer experience. Or if you're just trained right, you'll use these laws as is, but it's really the trainers that really have a good understanding of these gas laws. So that law I just showed you was Charles' law. Charles' law is that volume over temperature equals volume over temperature. And these 1s and these 2s, what that stands for is 1 is your initial states, 2 is your second states or your final states, however you want to think about it. Charles was a hot air balloonist, so he loved the idea of transportation of humans through the upper atmospheres via a hot air balloon. But he wanted to control the relationship. He wanted to understand it. If you think about it, if you just take off in a hot air balloon, you're dependent on the currents and trying to figure out where you're going to land. That's kind of important. You don't want a bunch of farmers with pitchforks to see you land and try and burn your balloon to the ground. That happened a lot back when they were learning how to hot air balloon. But the idea is as you heat up the air inside of the balloon, the volume is also going to increase. So as you increase the gas's temperature, those molecules start moving around a whole lot more. So what's going to happen is they're going to seek to expand the volume. But if you notice this hot air balloon, once it's expanded, it can't get any bigger. Okay, it's a finite volume. So what happens is that gas will come out the bottom, making it so now there's less molecules inside the hot air balloon. And because of density, things that are lighter or less dense, they're going to rise. Things that are more dense will sink. It's the same way as you throw a rock into a lake, it's going to sink. So with Charles' law, he realized as you increase that temperature of the gases inside the hot air balloon, those gases are going to seek a bigger volume, which is going to expand some of the gases out of the balloon, and the balloon is going to rise. And so he really used this relationship between volume and temperature to control his balloon in the air. There are a couple really good animations on Wikipedia, everybody's favorite public domain site, where this shows you that as you decrease that volume, decrease that pressure, your volume is going to change. So in this animation, you can see lots of weights are getting placed on the piston, and so that's signifying increasing in pressure. And so as you increase that pressure, that volume also changes and it goes down. So this is showing you if you hold your temperature constant, what's the relationship between volume and pressure. Increase pressure, decrease volume, and vice versa. And then here's the other rule, so Charles' law. The idea is as you heat up a substance, those molecules start moving more. If you hold that pressure constant, then that means their volume is going to expand. So increase temperature, increase pressure. Sometimes I'll go to elementary schools and do a demonstration. It's a lot of fun because the kids are like, "Ooh, science! This is great!" And I always bring, the whole goodie bag full of tricks, and it's a lot of fun. But one of my favorite experiments I do with the students is I have a little cooler, and typically it's like one of those 10 inches by 10 inch coolers. I mean, we're talking a little styrofoam cooler. And I will hold up a balloon that's been inflated, and I'll say, "How many of these balloons do you think I can fit in the cooler?" And they'll ask, "Are they inflated? Are they big? Are they small?" And I'm like, "No, they look just like this. I stuck them in this cooler. How many do you think I can fit in this cooler?" And typically they'll say 5, 6, 10. Normally don't get the real answer, which is 80, 90, something like that. It's however many balloons I felt like blowing up that day. Because if you add liquid nitrogen, which is really cold, to a balloon, it will shrivel up tiny in size. It'll look sort of like this, where these nice big balloons are now nice and shriveled. And the reason for that is liquid nitrogen is really cold. So as you are decreasing your temperature, you're also decreasing your volume. So there's that direct relationship that you're able to show the kids, and they just love it. Mainly because, I'll take the styrofoam cooler and I'll dump it on the ground, and then they see all these balloons. As they start to heat up, they start to inflate. Some of them will pop, which is actually the same reason as to why balloons pop in a hot car, is as they're increasing in heat, they start to expand, and eventually they might expand more than the balloon shell can hold, and they go pop. Okay, so it's a lot of fun to watch. A lot of cool gas laws are governing this process, though. So this is the combined gas law, where you've got Boyle's law, which is pressure times volume, Charles' law, which is volume over temperature, and then the lesser known Gay-Lussac's, who's pressure over temperature. But truly understanding it lets you understand why some of the things you see in nature happen. Like, why do hot air balloons rise? Why do balloons pop in hot cars? So this is the concept behind here.